Welcome back. For this lesson, we're going to talk about various aspects of light in terms of color. Now, the first section is on what's called thin film interference. And when we say thin film, you want to think of, like, if you've ever blown bubbles, the thickness of the bubble solution, like how thin that is in the bubble wand. That's the example that we're going to be talking about. So when we see thin film interference, it's something that includes constructive and destructive interference of light waves, and it will result in the spectrum of colors that you see in a soap bubble or an oil slick. So if you blow some bubbles and you look at how the light hits it, you'll actually see a rainbow of colors in the bubble itself. Now, on those colors that you see, there is constructive interference when the thickness of the film is the odd number of quarter wavelengths. So it's really similar to when we talked about resonating links for music, but now we're going to apply that same pattern to colors. And this is where the light is most strongly reflected. So I have an example. So imagine that you've got your bubble wand, but we're going to look at it sideways. Okay. So the wand itself is right here. And then imagine that you've got a side view of the bubble solution. It sags a little bit because of gravity, so that bubble solution is actually thicker at the bottom of the wand than it is up at the top. So I chose the red color. It looks a little bit more pink on yours when you actually see a bubble, but we're just going to go with red. So light comes in, part of it gets reflected right away, and part of it gets refracted and then reflects off that back surface. So when we see this little section right here, that's going to appear to be a red stripe. Now the thickness of the bubble solution itself is 1/4 of the wavelength for red light. So if we wanted to calculate how thick that bubble solution is, we would say 1/4, and red has a wavelength of 700 nanometers. And this would be equal to 175 nanometers. So whenever you have a bubble that's 175 nanometers thick, you're going to get a red stripe. Now, if you keep looking, that pattern will happen again, where some of the light gets reflected right away, some of it refracts through, and then reflects off the back surface of the bubble solution. And you'll get another red stripe when the thickness of that bubble solution is 3/4 of red's wavelength, which was 700 nanometers. And in this case, it would be 525 nanometers. So if our bubble is big enough, we can follow that pattern of 1/4, 3/4, 5/4, etc. And each time the thickness of our bubble solution is one of those fractions of red's wavelength, we're going to get a red stripe. Now in your picture, you should have another example of a blank bubble solution. So we'll do a different color. So let's pick violet next. Violet light comes in, part of it reflects off the front of the bubble solution, part of it goes through the bubble solution and reflects off that back surface. And then we would see a purple or a violet stripe. Now the thickness of the bubble at that particular spot would be 1/4 of violet's wavelength, which is 400 nanometers. So whenever we have a bubble solution that's 100 nanometers thick, you would see a violet or a purple stripe. That same thing would happen again. Part of it would reflect off later on in the bubble and then reflect off that back surface, and we would get a second violet stripe when the thickness of our bubble solution is 3/4 of violet's wavelength. So whenever we have a bubble that's 300 nanometers thick, you're going to see a violet stripe at that point. And so this would work for any color. So on the test, you would have a multiple choice question where I would say, you see the second stripe or the third stripe of yellow or green, and I would give you that color's wavelength, and then you have to calculate how thick the bubble is at that point. And in general, as the thickness of the film changes, you get different colors because the colors have different wavelengths to them. And then you should also see that as the thickness increases, the color with the shortest wavelength, so at the violet end of the spectrum, is most strongly reflected. You're going to see that one first. And the reason that you do not see certain colors is because of partial or total destructive interference. Remember, destructive is when the waves cancel each other out. And then if your bubble happens to start to appear black or gets a gray tint to it, then it's going to be too thin to produce any kind of constructive interference, and that's when your bubble pops. And then just in general, the colors that you see, remember they are produced by constructive interference, and then the colors that you don't see are destructive interference. So if you want to see these bubbles, you can come in and I'll show you up close and personal what those colors look like. For Roman numeral 5 on refraction, we actually have already had this when we studied our lenses chapter, so just take a moment and review that refraction is when light bends as it's going from one material to another. I happen to draw this one bending toward the normal, but it could also have refracted outward away from the normal. Just depends on the index of refraction of my materials. So review that you can calculate index of refraction by finding the speed of light in a vacuum, which was 3 × 10⁸ meters per second, and then you would divide that by the speed of light in that particular material that you're examining. And that answer would give you the index of refraction for that particular material. Remember, the index of refraction should be greater than or equal to 1, and it does not have any units. The other thing that we studied when we talked about refraction before was Snell's law, and that's where you have light traveling from one material into another, and you're able to calculate the angle at which that light is going to bend from one material into the other. So go back and review your notes from this section because you might see a question or two pop up from Snell's law or index of refraction. The last topic for this section is something called total internal reflection. Now, in order to understand that, we need to know what's called a critical angle. Now, the definition for a critical angle is the incident angle that causes a refracted ray to lie along the boundary between two medium. What that means is our refracted angle is specifically going to be 90 degrees. So I walked you through a derivation of Snell's law, and since the critical angle is the incident angle, that's the one we're solving for, so I made that substitution on the incident side. And if you were asked to calculate the critical angle for a material, you would simply divide the index of refraction for what it's traveling into over the index of refraction from the incident side where it's coming from. And then you also want to take the inverse sign in order for that to happen. Now, one of the nice things about this formula is you really can't screw this up. If your calculator is in degree mode, and let's say you forget which order to divide the two index of refraction values, if you mix those up and put them in the wrong order, your calculator is going to give you an error message. So if that occurs, that means that the particular material that you're looking at doesn't have a critical angle. And if you know that a critical angle should occur, then you've probably mixed up these two things. So you just need to go back and switch them and put the index of refraction for the refracted side on top and the incident side on the bottom. So I have an example problem for you. We're going from diamond into crown glass, and you're given the index of refraction value for each of those. Now we're asked to find the critical angle for this boundary. So in order to find that critical angle, we would take the inverse sign of the index of refraction for the refracted material over the index of refraction for the incident material. And in this case, since we're traveling from diamond into crown glass, the from gives us the NI, so that would be 2.42 on the bottom. And then remember the into is the refracted side, so that would give us 1.52 on the top. In this case, you should get a critical angle of 38.9 degrees. The next thing is total internal reflection, and it's just what the term means. All of the light will be reflected internally, so no light will be able to escape. And this is something that occurs when light travels from a more dense medium into a less dense medium. So you want to compare the index of refraction values when you look at those densities. Also, the angle of incidence has to be greater than the critical angle for that particular material such that all of the light will reflect back into the region of the more dense medium, so nothing actually escapes. So if we look at a picture, we've got different stages here. For all scenarios, we're going to be traveling from water into air, so from more dense into less dense. If our angle of incidence is less than the critical angle, then light is allowed to escape and you would see a refracted light ray. If we widen that incident angle and make it equal to the actual critical angle for water, then the refracted ray would lie along the boundary and we get a refracted angle of 90 degrees, and this is called the critical ray. If this occurs, it's going to look like the edge of our boundary is glowing. And then lastly, if our angle of incidence is larger than the critical angle, then the light will simply reflect off of that boundary between the water and the air, and all of the light stays inside and the law of reflection will apply. Again, I do have some demonstrations, so if you would like to see these things in person, you're welcome to come into the classroom anytime and I can show you some different examples. Here, and I believe this picture is in your notes as well, we have the importance of a diamond's cut. So when we look at the angle of incidence when it hits the boundary of a surface, if the angle is larger than the critical angle, then that light is just going to reflect internally. And in the case of a diamond, it'll keep reflecting and bouncing around until it comes back out, and it actually makes the surface of the diamond look a lot shinier because you're going to have that light reflecting out. If you have a different cut, then some of that light could refract and go out the other end, and then you're just letting that light escape. You're not going to actually be able to see it come out on the side that you're viewing. And then we have the same thing here. If we were to take a jug of water and shine a laser beam through it, if we poke a hole in the jug and let the water escape, then that laser beam can simply reflect all the way through, and you would be able to see those internal reflections at the boundary all the way down. And then again, I do have some circus toy demonstrations, so if you wanted to come in and see those. But the idea is that light would come up through the bottom, and then it just keeps bouncing inside, and it goes through a succession of internal reflections until it comes out the end, and then the tip is going to look like it's glowing. So that's another thing that you may want to take a look at when you're in the classroom. And that's it for this lesson.